Hello everyone. Today's lecture will be about chemical calculations part 1. So before we begin the lecture, we need to understand the term mole. So to understand the term mole, we have to understand the term the molar mass. So what is the molar mass? The molar mass of any substance is its relative atomic mass expressed in grams. So the relative atomic mass is the atomic mass of any substance which you get from the periodic table, right? So if you want to express the molar mass of something, you have to basically express it in terms of the relative atomic mass of the substance expressed in grams. For example, sodium has a molar mass of 23 grams. Why? Because 23 is the atomic mass of sodium that you can find from the periodic table. And 23 grams of sodium, because it is the molar mass, that means it is the relative atomic mass expressed in grams. So sodium has a molar mass of 23 grams. What does it mean? That means 1 mole of sodium atoms contain 23 grams of sodium. 1 mole of sodium atoms contains 23 grams of sodium. So in 1 mole of sodium atoms, you will find exactly 23 grams of sodium. So whatever the molar mass is, that is the exact amount that you will find in 1 mole of any substance. Similarly, 1 mole of oxygen atom contains 16 grams of oxygen. Why? Because 16 is the relative atomic mass of oxygen that you will find from the periodic table. So 1 mole of oxygen contains exactly the molar mass of the oxygen. So 1 mole of oxygen contains 16 grams of oxygen, while 1 mole of oxygen molecule, this was oxygen atom, right? Oxygen doesn't usually exist as an atom, it exists as a diatomic molecule. So 1 mole of oxygen molecule actually contains 16 into 2, which means 32 grams of oxygen. Why did I put 16 into 2? Because oxygen, the mass of one atom of oxygen is 16, but because there are two atoms in the diatomic molecule, that means we have to multiply this with 2, and that will give us 32 grams of oxygen. So if I say 1 mole of oxygen atom, it means 16 grams of oxygen is present in 1 mole of oxygen atom. But if I say that 1 mole of oxygen molecule, that means 32 grams of oxygen are present in 1 mole of oxygen molecule. Okay, so let's move on to the calculation of moles for solids. Okay, so if you wish to find the mole of any solid, you have to use this formula. Number of moles is equal to given mass by molar mass. So the given mass would be given in the question, and the molar mass you have to find from the periodic table. So the molar mass is the, like we learned, the relative atomic mass expressed in grams. The sample of sodium has a mass of 46 grams as per the question. Okay, so this is given in the question, and the molar mass is, like I said, the relative atomic mass expressed in grams. So the relative atomic mass of sodium is actually 23. That's something we know from the periodic table. So the molar mass of sodium would be 23 grams per mole. Now, why do we write grams per mole? Because it contains 23 grams in 1 mole of oxygen. So every mole contains 23 grams. That's why the unit is grams per mole. And the given mass is 46 grams as per the question. So you put that in the formula, you get 2 moles. Then calculating moles for gases. In here, that solid, the calculation was related to mass, but in here for gases, the mole number would be it would be related to the volume of the gas, how much volume the gas occupies at room temperature and pressure. Okay, so 1 mole of any gas at room temperature and pressure, what does it do? It occupies a volume of 24 dm cube or 24,000 cm cube in room temperature and pressure. So room temperature pressure, what does it mean? It refers to 20 degrees Celsius temperature and 1 atm pressure. That's what room temperature and pressure refers to. So any gas, 1 mole of any gas at room temperature and pressure will always occupy this much volume. Okay, so now we move on to the calculations. Number of moles is equal to given volume by molar volume. So let's say in this question, the sample of gas has a volume of 48 dm cube. That's given in the question. That's the given volume. And the molar volume, like we've learned here in the first line, that the molar volume refers to how much volume is occupied by 1 mole of the gas. So 1 mole of any gas at room temperature and pressure always occupies a volume of 24 dm cube. So in here you divide this dm cube value, you divide this given volume by the molar volume. So 48 by 24, as you can see, the unit is expressed in dm cube per mole. Why is it dm cube per mole? Because 1 mole of any gas at room temperature and pressure contains 24 dm cube. So it's dm cube per mole, per each mole. Okay, so we get, if we use this formula, we get 2 moles for this specific sample. Now let's move on to consider calculating moles in aqueous solutions. So you can find the moles from here, more like you can find the concentration of aqueous solutions from here. in one of three ways. You can either express the concentration in moles per dm cube, or you can express this in grams per dm cube, or you can express this in parts per million, depending on what you are asked. So if you want to express this in moles per dm cube, you have to divide the number of moles of the substance which you're dissolving in the water by the volume of the water in which you're dissolving it. If you want to find the concentration in grams per dm cube, we divide the given mass of the substance which you're dissolving by the volume of water in which you're dissolving it. And the last one, this one is a bit specific. This one is only applicable for very, very small concentrations. When you have to find the concentration of something which is very light, which is very less dense. Okay, so this is why you have to multiply this thing with 1 million. So what do we do? First, we divide the given mass of the solute, the thing which you're dissolving. You divide the mass of the solute by the mass of the solvent in which you're dissolving it, and you multiply that with 1 million. This is why we call it parts per million, because we are finding the ratio of how much of the solute is dissolved and how much of the solvent, and we are multiplying that with 1 million to get the concentration in parts per million. The next thing is about the examples related to finding the concentrations. So the first question, 58.5 grams of sodium chloride are dissolved in 2 dm cubes of water to make a solution. Find the concentration in moles per dm cube and in grams per dm cube. So first, let's find the concentration in grams per dm cube, because that is very straightforward. The given mass of the substance is 58.5 grams. Okay, so we use the first formula, this one, grams per dm cube, given mass by volume of water. So given mass is 58.5 grams and the volume of water is 2 dm cube of water. So we divide this, we get 29.25 grams per dm cube. That's the concentration in grams per dm cube. Now, what if I want to find the concentration of this thing in moles per dm cube? So first I have to find how many moles there are in these many grams of sodium chloride. First I have to find how many moles there are actually present. Okay, so as you can see, 15.5 grams of sodium chloride. So if I want to find the number of moles of sodium chloride, what do? I use that formula, given mass by molar mass, which we learned in here, this one. Given mass by molar mass, this is applicable for a solid, and as we know, sodium chloride is a solid. So from here I can find the number of moles of sodium chloride, which is the given mass 58.5 divided by its molar mass, and the molar mass is basically a combination of both sodium and chlorine, because it contains both sodium and chlorine. So it has 1 of sodium, that is why we used just 23 ones, because it contains 1 atom of sodium, and it also contains 1 atom of chlorine. That's why we also added 35.5. So 23 is the molar mass of sodium, which we got from the periodic table, and 35.5 is the molar mass of chlorine, which we got from the periodic table as well. So we divide this, we get 1 mole. So what does it mean? It means that 58.5 grams of sodium chloride actually refer to 1 mole of NaCl. 58.5 grams of NaCl actually refer to 1 mole of NaCl. Okay, so this is the concentration in grams per dm cube, and if I want to express this in moles per dm cube, what do? I found the number of moles which was present in 58.5 grams of sodium chloride, and then I divided this by the volume of water, which is 2. So 1 mole dissolved in 2 dm cubes of water, we get 0.5 moles per dm cube, the concentration of this in moles per dm cube. Now, if I want to express concentration in parts per million, this is one such question related to that. 5.85 grams of sodium chloride dissolved in 1000 grams of water. Find the concentration in parts per million. So in here we know the mass of the solute that's being dissolved in this much mass of water, right? So in the formula, which was related to parts per million, what did it say? It said that you have to divide the given mass of the solute by the given mass of the solvent, multiply that with 1 million. So the given mass of the solute is 5.85, and the mass of the solvent is 1000. Put it here, and then you multiply this with 1 million. That will convert this thing into parts per million. So we get 5850 parts per million. So like I said, this is applicable for very, very small concentrations, much smaller than this. In here I was actually giving a pretty standard concentration. It should actually be much smaller. It could be something like 0.00585 grams dissolved in 1000 grams of water. That would have made this a bit more significant. Okay, so yeah, Avogadro's constant, this is the last thing that we have to discuss. So this is a constant which was basically propounded by Avogadro himself, Mr. Avogadro. So he did a lot of experiments, of course. He carried out a lot of experiments, he wanted to find out how many atoms there are present in 1 mole of any substance. We know that 1 mole of any substance contains its molar mass of, the substance. So that's why we say that, 1 mole of sodium means 23 grams of sodium, right? Because, that's the relative atomic mass expressed in grams, the molar mass. So 1 mole of sodium contains 23 grams of sodium, but it doesn't give us the number of atoms. It just gives us the mass. So Mr. Avogadro, he carried out, a series of experiments, and he found out that 1 mole of, anything contains these many atoms or molecules or ions. Now, why do I say atoms or molecules or ions? Why do I not say anything fixed? Because it refers to a wide range of particles depending on what is mentioned in the question. So, for example, 1 mole of sodium atoms. The question has mentioned that it is atoms. So 1 mole of sodium atoms refers to these many atoms of sodium. So if you have 1 mole of sodium atoms, that means you have these many atoms of sodium present in this amount. Okay. Now, if you say 1 mole of oxygen atoms, again, it's atoms. So it will refer to these many atoms of oxygen. So if you are referring to atoms, it will refer to atoms. Okay. So 1 mole of sodium atom means these many atoms of sodium. 1 mole of oxygen atom means these many atoms of sodium. Sorry, these many atoms of oxygen. These many 1 mole of sodium refers to these many atoms of sodium, and 1 mole of oxygen refers to these many atoms of oxygen. Now, what if we take our discussion towards molecules? So 1 mole of oxygen molecules, what do they refer to? 1 mole of oxygen molecules refers to these many molecules of oxygen. That's the point to be noted. Molecules. See, it is flexible. The Avogadro's constant, it is a value, but it doesn't refer to any specific thing. It varies depending on what you are dealing with. So in here we dealt with 1 mole of oxygen molecules. So that means what? These many molecules of oxygen are present in 1 mole of oxygen molecules, right? The last one, 1 mole of sodium ions. So this can also refer to ions. So 1 mole of sodium ions, what does it refer to? Same thing. These many ions of sodium. So this number is a flexible number. It is not fixed to any specific type of particle. It's spread out to a wide range of particles. So if you're dealing with atoms, 1 mole of any thing's atoms, it will refer to those many atoms of that substance. If you're referring to molecules, it will refer to those many molecules of that substance. And if you're referring to ions, it will refer to those many ions of that substance. Okay, so depending on the question in hand, we have to adjust our particle in Avogadro's constant. So this wraps up part 1 of chemical calculations. Part 2 will deal with the calculation of empirical formula and the molecular formula of a substance. And to do so, we have to carry out a series of steps to actually calculate the empirical formula. So that's for next class. Thanks for listening to this lecture.